Welcome back to another LeetCode video. We're looking at 417 Pacific Atlantic water flow. I'm going to explain you real quick what this problem is about, and then I'm going to show you how to solve it. It's actually quite simple, so it should be a quick one really to explain this. So what are we dealing with? Well, we're giving a height map as in the form of a two-dimensional array. I'm just going to call this grid. So we're giving a grid that is two-dimensional and that contains heights of a mountain range. So you can see here, this each cell has a different height, and we are being asked that if it rains onto this mountain range, from which cells in this grid can the water flow into the Pacific Ocean and into the Atlantic Ocean at the same time. And you can imagine that if water rains on this cell with the value 7, with the height 7, water can flow always downhill. So it could go into this cell with the height 4, 2, and into the Pacific Ocean. It could also go up here into the Pacific Ocean. Similarly, you could argue that water can also flow here into a cell of height 1 and into the Atlantic Ocean. So all of the cells that are marked here in yellow are the cells that have a water path downhill into both oceans. The task is to find out what are these peaks or what are these cells from which the water can flow into both oceans. If you take, well, the first question is, how can you determine that? Well, I've just shown you that you could look at into which cells neighboring cells can the water flow. And you could imagine that you could just do a breadth first search or a depth first search traversal to figure that out. One thing to note is if two peaks have the same height and they're adjacent to each other, then water can flow into either direction. So from this peak with height 4, water can flow to peak with this neighboring peak with height 4 as well. And I've already sketched the solution idea, which is for every single cell, you figure out into which ocean the water can flow. But the problem with that is, if you start, for example, from this cell with height 5, do you want to find just one path into each ocean, or do you want to find a path into both oceans at the same time? So if you had to figure out for every single cell if you could go into either ocean, that seems a little bit complicated. So is there a way to reformulate this approach so that it is easier conceptually to put into code? Well, how about we go the opposite direction? How about we start at the coast and we go as high as we can and we collect all of the nodes that we can reach by only going up or walking on a plateau between two heights or peaks of the same height. If we did that, then if we start at the Pacific Ocean, for example, we would start from all of these coastal cells, and we would try to take a step into all of the neighbors. And of course, because we don't want to revisit nodes that we've already visited, we need to keep track of the nodes that we've already visited. So we will then eventually, after one iteration, we will have, actually let me paint this here. I think that would be easier to understand. So if we start at all of these cells, and we put all of these cells maybe into our depth traversal or breadth traversal tree, then in the next step, we would reach all of these cells. Because we are only going up. No, actually, that's not quite correct. So from 5, we can only go up to 6, but that's already basically in our queue, so we're not going to go there. From 6, we can go only to 7. So 7 will become part of our visited nodes. From 2, we can go to 4. From 3, we can't really go anywhere, but we can go from 1 to 2. 2 is already in our list, but we can go from 2 to 2. So This one goes into our queue. We can go from 2 to 3, that's going uphill as well. We can go from 3 to 4. And so now we have these nodes also in our in all of the nodes that are reachable from the Pacific Ocean coast. Now we repeat the step, and when we do so, we start to include this 4, and we go from 3 to 5 or from 4 to 5, and we include that node. Now we've kind of reached the end, because now all other nodes that are a neighbor of the nodes that we visited are all smaller. So we're not reaching anything. So in conclusion, all of these nodes that are marked are reachable from the Pacific Ocean. Now we can do the same thing when we start from the Atlantic Ocean. And let me just clean this up a little bit. Right, so I'm just going to draw this line so we know which ones were reachable from the Pacific Ocean. And now we start the same thing from the Atlantic Ocean. We're putting all of the nodes that are on the Atlantic coast into our initial list of nodes that we can visit. And then we ask ourselves, which ones can we visit by going uphill? So we can go from 1 to 1. We can go from 2 to 4. We can go from 1 to 3. From 5 and 4 we're already here, but we can go from 4 to 4. And so that would be the first. And we can go from 5 to 6 as well here. And we can go from 1 to 7. So now we've included all of these green ones. Now there's another final step where we can go to this node with the 5. Well, if we now draw this line again for all of the nodes that we can visit from the Atlantic coast, we see that there's now an overlap between the nodes that can be visited from the Atlantic coast and the Pacific coast. And this is basically our solution. So the approach is really to do 2 traversals of the grid where we put all of the coastal nodes into the queue in the beginning, and then we just start to traverse the grid only uphill. And we get 2 sets of nodes, and then we just calculate the intersection of these 2 sets of nodes, and that's going to be our result. So let me put that into code. We're going to talk about the space and time complexity analysis in a moment. Space, right. Now the problem gives us some specific instruction on how to return the result. That is noteworthy to know. So it basically wants the coordinates of the nodes that lie on this peak of this range of mountain peaks as an array. So here you can see the node at position, let's see, I think they have the Y first and then the X. So this is position 0, 4. So this is row 0, 0, 1, 2, 3, 4. This is this 5 and so on. So they just return the coordinates of those peaks inside the grid. All right, cool. So let's structure our problem-solving approach. We know that we have to have a function that returns us our neighbors, because we need to be able to fetch the neighboring nodes. If we want to get the nodes of a coastal neighbor, we don't want to return invalid nodes or invalid cells or invalid coordinates. So we need a function that does that for us. So we're going to have a function get neighbors, and I'm going to give it a tuple that has an XY coordinate. And we're going to flesh that out in a moment. Then what we will need is we need a function that does the traversal for us, because remember, we need to traverse, well, we need to do 2 searches through our grid, one from the Pacific coast and one from the Atlantic coast. So we don't want to duplicate the code. So we're going to have a little helper function. You can name that however you like. Maybe we should name it, get reachable peaks to insinuate that we're going upwards, and we're going to give it a seed, which would be a list of nodes. And in that, we will construct a set, a visited set. And in the end, we will return that set. So, yeah, and we'll have to do something to implement that. Now, all we need to do now is we need to put all of the, well, coastal cells or coastal nodes into our seed. So we're going to have a little seed array when we will construct it. And then we will compute all the nodes that we can reach from the Pacific sides. And we will do exactly the same thing for the ones that we will get from the Atlantic coast. Atlantic. And now finally, what we have to do, we just have to, well, construct the result. And then we return the result. Okay, so this is the high-level structure of our solution. I think that should lay it out quite quickly. The good thing is that it's very simple now. You just need to implement all the different individual parts. And it's very difficult to really mess that up. And it's very easy to check if any of those individual implementation parts are correct or not. Which can help you in an interview when you try to, show a systematic approach and make it easy for yourself to debug. So that's what I would recommend. Well, I think maybe the easiest is to start actually with the getNeighbors method. But if we want to approach the problem from where we start, we should probably construct the seed first. Maybe that'll help us to understand exactly how these things look like. So how do we put all the Pacific nodes or cells into the seed array? Well, we're just going to iterate over all of the x coordinates here, because we know that the top row of our grid is going to be on the Pacific Ocean coast. And, well, we need to iterate over the width of the grid. Well, we don't know yet what the width is. So we need to define that. We need to define the width and the height. And we can do that like so. Grid. The width is always the length of the first row of the grid, and the height is just the number of rows in the grid. There we go. Width and height. Now we can iterate over the width, and we know that into seed we can just add seed, append. Well, I said we're going to deal with tuples. So I'm going to do that. So we just put an x, and, well, the first row means the y coordinate is 0 for the first row. So that's what we do. Now we also want to add these nodes. And similarly here, we just iterate over the y coordinate. And all we need to do is put the height in it. So we iterate over the entire height of the grid. And we're appending the node at position x equals 0 and y as y. Now we're adding this node twice, right? Where x is 0 and where y is 0. We're adding that twice. But it doesn't really matter because our visited will be a set in the end. So we don't really care. It doesn't make a difference at all if we try to compute the path from here twice or not. And you will see that because we're going to check against visited nodes, we're not actually going to compute the path from the top right cell twice. So that's that. And now for the Atlantic coast, it's actually very similar, except now what we do is we have to put in height -1 and width -1 where we had the coordinate 0 before. That's it. So that's how we initiate the seeds. Now when we iterate over the results, we expect that our visited set contains the same type of position where we have an xy tuple. So we just need to compute the intersection. You can do that in Python with, Python set operations if you want to. I believe it would be XOR something, Pacific XOR Atlantic, or you could do it by hand. I just like to do it by hand just to make it explicit for position in Pacific. If position in Atlantic, that means we found a node that is both reachable from the Pacific and from the Atlantic. So that means it belongs into our result set. Cool. And now, because if you read this problem carefully when you do it yourself, you'll see that the X and Y position are inverted. So what I actually have to do, I have to put them in reverse order in the result. Otherwise, you're going to get an error. All right, so now we've implemented all of that. Now we need to implement the graph traversal, and we need to implement the get neighbors. I'm just going to implement the get neighbors first because that's an easier, smaller part. So this is a small piece of code that you will have to write repeatedly when you go through all kinds of different LeetCode problems. For me, I've already memorized it. So how do I quickly iterate over all of the neighbors in all 4 directions of a node? I can do that in one for loop for px or neighbor x and neighbor y in zip. Zip is a function that allows you to basically traverse 2 arrays in parallel, so that the first one assumes the value in the first array and the second one assumes a value in the second array, and you just iterate over all of them. And what you can do here is you can just put in, well, the first coordinate is going to be x minus 1 and y. So that means this is just to the left of the node. So if we take node 5, this would point to the position of the node where the 4 is. Now the second one is where we leave the x untouched, but we change the y to y minus 1. And that is just above the node with the 5 here. And you can see how that iterates. So now we have to do x plus 1 and y stays the same. And finally, we have to go and look below the xy node, which is at position x and y plus 1. So we're now iterating over all of the 4 neighboring positions of a node. All we need to do now is we need to just check if that node is still in bounds of our grid. So if nx is smaller than 0 or the x position is larger or equal than width, we're just going to ignore it because it's out of bounds. Same for the y coordinate, except for the y we check if it's larger or equal than the height. And if it is, we're just going to continue and ignore that completely. Now, because we only want to go uphill, we could put that check to go uphill in here as well, right? So get uphill, but it's not strictly uphill, right? We also want to be able to visit same elevation nodes. So uphill or level neighbors. So that would be a better description. Your choice if you want to name it that way. It's probably not strictly necessary, but it makes it a little clear. So we also need to determine the height of the position. And the current height is the same as grid at position y and x. That's going to be of the height of our current cell. And then we check if height is smaller than, well, if the height of the new node is smaller than our height, then we're just going to ignore it. Because we want to climb uphill, remember? So we're checking if grid at position ny nx is smaller than the current height, or we could just put it in here, doesn't really matter. Then we're just going to ignore it. We're not going to go downhill, right? So when we've reached 5, we can't go anywhere else because all the neighboring nodes are smaller. So we're running into this continue statement here. Cool. And now everything's fine. We found a neighbor that is actually valid and that is higher than our current cell. So all we need to do is we need to add this to our return. And, neighbors. For the return, we just have an array. Neighbors equals empty array. And now what we do is we just append that node as a tuple. Next y and next x, next y position, and then we just return the neighbors in the end. So yeah, that's pretty much it. So that concludes our little get neighbor helper function. Now let's flesh out the graph traversal or the grid traversal function. Now we're going to need some kind of data structure to iterate over all of the candidates in our queue. I like to always use the same pattern, which is just to import from collections, import the deck. I think the deck doesn't have to be imported in LeetCode because it's already available. If it's not in your environment, you have to import it first. So we just initialize a queue, and we're going to put all the seed elements into that queue. So that's what we're going to do. And then we're just going to iterate while queue. While we still have elements in our queue, we need to process them. And yeah, that is very simple. All we need to do is we just pop out the next node. So we will say position. We're just going to pop it on the left out of the queue. And then we just check if pause in visited. Well, we're going to ignore it because we've already visited that node. This is the classic breadth first search approach. Next, we need to add it to our visited list so that we don't visit the position again. And now all we need to do is just iterate over all of the neighbors and add them to the queue unless we've already visited them. Or, well, actually, we don't have to check if we visit them or not because we will once we pop them out again. So for next position in get uphill or level neighbors of our current position, and we're just going to do queue append next position, and believe it or not, that is everything you need. So I hope you can see how this algorithm now propagates through the entire grid. As long as we have an uphill neighbor that we haven't visited, we are going to add that node, that neighbor node. Well, we're going to add all the neighbors that are uphill and have not been visited and process them. Sorry, I misspoke. We're going to add all the uphill neighbors, and then we're trying to process them, and we're not going to process them if we've already visited them. Otherwise, we will continue to process them by looking at their neighbors, etc., etc. So that's how that works. That's how that works. And now let's have a quick look at the space and time complexity. So we're going to iterate. So every, let me see. So yeah, let's first define our width and height. So n is our width and height of the grid. Let's reverse it. M and M are the width and height of the grid. So obviously, if we look at where we start, so the seed array will contain m plus n elements. However, every time we call our reachable peaks function, it means we're going to potentially, in the worst case, when all height elevations are the same, are equal, we're going to traverse the entire grid, which means we're going to traverse m times n cells each time we call it. And we're doing it twice. So that means the time complexity is always going to be the width and times the height of the grid. And in terms of space, well, worst case is that all cells have the same elevation. That means all of them are going to end up in our result set. So it means we have the same worst case time and space complexity. So the complexity is linear in the total number of cells in the grid, but if you express it as width and height, it's basically width times height number of nodes in the grid. Now let's see if I made an error in the implementation. I don't think I did. Maybe I have a typo somewhere, but the logic should be sound. So let's run it through the test to see what happens. Wrong answer. Okay, that is not good. Checking. Let me see. So I'm getting different length of the output, but I'm also getting some correct cells. So that leads me to believe that maybe the error is in the way of how I construct my neighbors. So I'm going to check that. -1 plus 0. So there's not an error. That is correct as well. Now we have y plus 0, y minus 1, y plus 0. Oh, here we have an error. That's a typo. That should be a y, not an x. I'm just going to check the other conditions. This looks correct. This looks correct. And this one looks correct as well. Yeah, so I think that could have been it. So let's see. Okay, so that looks good. And let's submit it to see if it passes all of the tests. And there you go. So this is, I believe, the optimal space and time complexity, because that's the worst case scenario. If everything is the same, you have to visit at least every node once. and you have to return every node in the worst case. So you can't really go better than width times height. All right, this concludes this video.